So if we think back, the purpose of section 2.1 was to motivate limits, to tell you why you should care about them. Then the point of section 2.2 was to help illuminate what a limit really is and what it represents. And that brings us now to section 2.3, where we'll look at properties of limits and come up with some methods for actually evaluating them, which don't depend on having access to the graphs of whatever functions you're dealing with. Because, to be honest, it's a lot of work to come up with a graph, or it requires the use of software or some sort of graphing device, which I did promise you that you wouldn't need those for this course. So it'd be awful nice if we had a method of working these out by hand that didn't require us coming up with the graph somehow. And in fact, in most cases, that's going to be true. And in a lot of cases, and in fact, all the cases that we're going to be interested in, we can do them by hand. So it works out really nicely. So we're going to start with a couple of observations. So let's say I had two fixed numbers. So I'm going to say for any constant values, I'll say A and C. And of course, they're real numbers. So we'll start with that in the background. I should have made a comma here. And I'm going to make two statements. And the first is going to be about the limit as x approaches a of x. Okay, let's think about what that notation means. What we're really saying is here is we want to take the limit as x approaches a of x. And if you think about a limit as the answer to a question, the question would be, what happens to the values of x as x gets closer and closer to a? Well, that almost sounds like a question that answers itself, right? As x gets closer and closer to a, the values of x get closer and closer to a as well. Really what it comes down to is this. If the function you're dealing with is exactly the same as your limit variable, then the limit is going to evaluate to whatever your limit variable is approaching. So in this case, the answer is a, right? So as the values of x get closer and closer to a, the values of x also get closer and closer to a, and that's why we can write that. So our second observation that we'll write down is the following. So if I take the limit as x approaches a of the constant function c, because constants are still functions as well, right? A constant function c is a function of x. Its graph just happens to be a flat line. And it turns out no matter what the value of x is, c is always equal to c. It's independent of x, right? So what happens if I try to work this limit out? Well, you're basically asking a question again. You're saying, what happens to the values of this function as x gets closer and closer to a? Well, the values of this function are all going to be c, no matter what. So c really doesn't care what's happening to a. It's always going to be c. So this limit is also going to be something that you can just write down right away. Okay, and if you want, as an exercise, you could verify these by drawing some graphs. Right? For this one, you could just draw the graph of the identity line and use the graphical method for evaluating limits, and you can show that this limit is equal to a. And then here, just draw a constant function. Draw a picture of a constant function and see what happens as x gets closer and closer to some fixed x value a. And you'll see that you're going to always get that constant c that you started with. Okay, so what do you do with those? Well, those two observations on their own might not be very powerful, but if you combine them with the limit laws that I haven't written down yet, but we're going to fill this space in with limit laws, then you can actually get a lot from just these two observations. Okay, so let's go over some of these laws. And so we're going to start with the assumption that we have two limits. So we have the limit of two functions as x approaches a. We get the limit as x approaches a of f of x, and a limit as x approaches a of g of x. So we're going to assume that both of these limits are already known in advance to exist. And if we work forward on those assumptions, we'll be able to state some pretty useful laws. So the first law we're going to state is that if I have the limit as x approaches a of the sum of two functions, f of x and g of x. So here what I'm doing is a little bit of noise outside. I think they're almost done. Okay, so I've got two functions, f and g. They get added together, and then we take the limit as x approaches a afterwards of all of this function. Well, it turns out you can break this up into two limits. I can work out the limit as x approaches a of just the function f of x, and then I can add that to the limit as x approaches a of g of x. So I'm turning a single limit problem into a problem that involves two limits, but each of those limits is a little bit simpler to work out, or at least in theory it would be, right? So that's the first law. Really what this is saying is that limits respect sums of function. sums of functions. The limit of a sum of two functions is the sum of the two limits of the individual functions. That's another way to phrase it. Okay, and property 2 really just says we have the same thing but for subtraction. So if I want the limit as x approaches a of the difference of f of x minus g of x, so I'm subtracting the function g of x from f of x first, and then whatever the result is, I take the limit of that function as x approaches a. Well, it turns out you can work that out by evaluating each limit separately and then subtracting the limits. So I can work out the limit as x approaches a of f of x, and then I can subtract the limit as x approaches a of g of x. Okay, so those properties are kind of, they go in a pair, right? They're basically very similar properties, but one's for subtraction and one's for addition. And there's one for multiplication as well. So if I take the product of f and g, and I take the limit as x approaches a, so I've got f of x times g of x, and I take the limit of this function as x approaches a, I can instead just take the limit of each factor separately. So take the limit as x approaches a of f of x, and multiply it by the limit as x approaches a of g of x. So you got one for multiplication as well. And you might be wondering already now at this stage, is there one for division? And certainly there is, but you have to be careful. And so let's state that now. So the limit as x approaches a of the quotient f of x divided by g of x, well, we can write that as a quotient of limits. That's the limit as x approaches a of f of x, and all of that divided by the limit as x approaches a of g of x. Now, but we have to be careful, because maybe this is 0, right? Maybe the limit as x approaches a of g of x actually ends up being 0. So in which case the right-hand side of this equation wouldn't make sense. So we should actually say, we should add this in, as long as the limit as x approaches a of g of x is not equal to 0. Okay, and if it is equal to 0, then this rule won't apply. Another really nice rule says that you can pull constant multipliers out of limits. So here's what that looks like mathematically. I'll write limit as x approaches a. If I have a constant times the function f of x, and I just multiply f of x by that constant, I'm going to get a new function of x. And I can take the limit of that function as x approaches a. Well, it turns out I can take that constant c and I can pull it right out of the limit and multiply it on after. So this turns out to be equal to c times the limit as x approaches a of f of x. Oh, my printer made a hiccup there. Okay, so that's what this is saying. So if you have a constant multiplier inside of a function and you're taking the limit of that function, you can pull that constant right outside, and this is what you get. And this is true for any constant real number c. And in fact, I won't write this down, but it may be interesting to you to know that you actually don't need c to be a constant in this case. It's good enough as long as c is independent of the variable x. That turns out to be good enough. Okay. All right. So if you apply property 3 to the case where f and g of x are the same, what you'd really get is f of x times f of x here. And this would really just be f of x all squared. But then you'd also have an f of x here. So you'd have the limit as x approaches a of f of x times the limit as x approaches a of f of x. So in that case, again, I'm talking about the case where f and g are the same function, the right-hand side of this would be the limit as x approaches a of f of x all squared. So let me actually write that down. So I'll add it in a note up here. If f of x equals g of x, this rule becomes the limit as x approaches a of f of x squared. I'll just put square brackets around the function to make it clear that it's the the entire value of f of x, the output from the function, is then squared, and then whatever this function is, that's the one you take the limit as x approaches a of. Well, it turns out that this is going to be equal to the limit as x approaches a of f of x all squared, right? And that's a direct consequence of this rule. If you consider the case where f and g are the same function, you end up getting this rule. And now this leads to another question. Well, if there's anything special about the power of 2, it would also apply for the power of 3. If I had f of x cubed, I could pull the power out of the limit and write this as the limit as x approaches a of f of x, and then cube the limit. And it works for any other power as well. So let's do that. Let's write that in as a property. This comes from repeatedly applying this rule. So the limit as x approaches a of f of x raised to the power of n. So just to be clear, that n is on the f of x. So if I take the limit as x approaches a of this power of f of x, I get the corresponding power of the limit of just the underlying function. Okay, and this works for any exponent n. Okay, and lastly, the last thing I want to write on this page is actually the particular case when f of x is the identity function, f of x is equal to x. So in particular, let's add a note. So if f of x is equal to x, this is called the identity function just because it just doesn't touch the input value. If you give it an input value, it just sends you back that same value as the output. So it's called the identity function because it doesn't make any change to whatever you plug into it. So what do we get if we rewrite rule number 6 with this function in mind? Well, we get the following. We have the limit as x approaches a of x raised to the power of n, right? Because I just replace f of x with x. And, well, then what do I get on the right-hand side? I'd have the limit as x approaches a of x, all in brackets, raised to the power of n. So this is a direct application of rule number 6. But if you remember one of our observations tells us exactly what this is, right? If you go back up to the beginning, we already mentioned if you have the limit as x approaches a of x, you get a, right? So from this observation, you can plug it in down here inside the brackets. This is really just a. So what this actually works out to is a to the n. And this consequence of rule 6 is actually going to turn out to be quite useful when we're dealing with polynomials, which we'll discuss in the next clip.